Hi everyone, this is Maths for Uni. Today we'll be discussing question 4 from MAT 2019. If you find this content helpful, then please consider liking and subscribing, as well as checking out our full Udemy course. The link is in the description. The question says, in this question, we will consider subsets S of the xy plane, and points A, B, which may or may not be in S. We will be interested in those points of S which are nearest to the point A, B. There may be many such points, a unique such point, or no such point. Part 1 of the question says, let S be the disk x squared plus y squared is less than or equal to 1. For a given point AB, find the unique point of S which is closest to the point AB. They give us a hint that says you will need to consider separately the cases when a squared plus b squared is greater than 1 and when a squared plus b squared is less than or equal to 1. So to start with, we have this disk S, which is the set of all points such that x squared plus y squared is less than or equal to 1. This is all of the points inside here, as well as on the edge of this circle here, which has a radius of 1. It will be quite important for this part of the question that we have the points on the edge as well. So, taking their lead, we should consider that we have, say, a point AB, which is, depends on the case, either here or somewhere out here, and let's call them case 1 and case 2. Case 1 corresponds to a squared plus b squared being strictly greater than 1, i.e. this point here is outside of the disk here, and then case 2 is a squared plus b squared being less than or equal to 1, where the point here is either inside the disk or on the edge of the disk. Case 2 is slightly easier than case 1, and so in case 2, we have our point AB, which is inside of the circle, and therefore the point in S, which is closest to this point AB, is AB itself, because precisely AB is in S. Case 1 is slightly harder, because now this point AB is actually outside of the set S. So where is the closest point to this point AB that is in the set S? Well, it will lie on this line here, but it will be the closest point along this line such that we remain in S, and therefore it will be the point on the edge of this disk S. So to find where this point is, we note that because it's on the line joining the origin to the point AB, it will look like AB, but we will need to divide by some factor. For example, if we divided by the factor 2, then we'd have the point which is halfway in between the origin and AB. So what is the factor that we should divide by to get the required point here? Well, the points on the edge of this disk are characterized by the fact that their x squared plus their y squared is exactly equal to 1. And therefore, we divide by the square root of a squared plus b squared, because then this point overall, which we can write as a divided by the square root of a squared plus b squared, and b divided by the square root of a squared plus b squared, will then have a distance of 1 from the origin. Therefore, this or this is the answer for the unique point of S that is closest to AB in the case of 1, which is a squared plus b squared is strictly greater than 1, i.e. AB is outside of this disk. This was part 1, and next we can discuss part 2. This says, describe without further justification an example of a subset S and a point AB such that there is no point of S that is nearest to AB. Now, because it says without further justification, that kind of indicates that we should use our work from part 1. Have a think about how to do this based on what we saw here. We need to have a slightly different subset S and a corresponding point such that there is no point of S that is nearest to AB. In some sense, we can keep getting nearer and nearer. Well, if you had a quick think about it, then I will tell you the answer. You can take a very similar set S to be the set of all x squared plus y squared that is strictly less than 1, i.e. we have this set here, except the edge is not included. We can write this by having a dotted line for our edge. Imagine standing on the edge, then you would fall through because of the dotted line. So this set includes all the points in here, but not on this edge here. Again, this has a radius of 1. We need not write any of this down, except for the actual answer, because we need not do any further justification. All they want to see is that you can think about what the set would be. Then, if we kind of use the cases that we have here, which case would result in an issue? Well, if we have a squared plus b squared being strictly less than 1, so slightly different from this, but with strictly here, not with the equal to case, then the point which is closest to that point AB, but is in S, would be the point itself. However, if we have a point AB such that a squared plus b squared is greater than or equal to 1, i.e. on the edge here, or even further away, then there would be no unique point in this set S which is closest to that point AB. I'll draw it out here, for example. Say you have a point in S that you think is closest to this point AB. Say you draw it on here. Well, then I can find a point even closer, namely a point in between here. And even if you come back and say, I can find a point even closer, we can continue playing this game of getting closer and closer to the edge of this circle, but we can never reach it because of this strict inequality here. This is an example of an open set, and if you do any higher level pure maths, you will see examples of open and closed sets. So this is an example that you can use to answer this question without any further justification. All you need to do is write down the set that we have here, as well as a point that would work. And you can even just write the point AB, as long as you write that a squared plus b squared is greater than or equal to 1. Part 3 of the question says, describe, again without further justification, an example of a subset S and a point AB such that there is more than one point of S nearest to AB. So again, because we have no further justification needed, it's going to be quite similar to what we've been considering so far. Again, I encourage you to have a think about a subset S as well as a point AB that you would consider. Continuing on, we can use the set x squared plus y squared is equal to 1, i.e. the edge of this circle only without having any of the points inside or outside. This time we need to choose a particular point in order to illustrate what we mean, and the best point to consider is the origin right in the middle here. Why is this? Because then every single point in S is exactly a distance 1 away from the origin 0, 0. Therefore, there is certainly more than one point in S that is nearest to this point 0, 0. In fact, there are infinitely many. Next, part 4 of the question says, let S denote the line with equation y equals mx plus c. Obtain an expression for the distance of AB from a general point x mx plus c of S. Show that there is a unique point of S nearest to AB. So we have this line with equation y equals mx plus c, and we have a point AB and a general point which is on this line, x with mx plus c, where m varies. Well, to find the distance between these points, we use the usual Pythagorean result, which is that the distance, let's call it d, is the square root of x minus a all squared plus mx plus c minus b all squared. This is an expression for the distance between these 2 points. Next, we need to show that there is a unique point of S that is nearest to AB. There is a useful trick here, which is to consider d squared, which is removing the square root, x minus a all squared plus mx plus c minus b all squared. If there is a unique point of S nearest to AB, then we can look at either of these 2 things to consider that. However, this one is much easier to work with because of the lack of square root. To get a unique point of S nearest to AB, we need to have a unique minimum of this expression here as x varies. However, this is a quadratic which has its x squared term as being m squared plus 1, which is certainly a positive number. And therefore, because it is a quadratic which has a positive x squared term, there is a unique minimum of this quadratic. As a result, there is a unique point of S nearest to AB. A unique point of S nearest to AB. Recall that S is the set which has the line y equals mx plus c. Next, we can look at part 5 of the question. It says, for some subset S and for any point AB, the nearest point of S to AB is given by the coordinates a plus 2b minus 2 all divided by 5 and 2a plus 4b plus 1 also all divided by 5. And we're asked to describe the subset S. Now this result is true for any point AB in the whole of the xy plane. Again, the point is a plus 2b minus 2 over 5 and 2a plus 4b plus 1 over 5. because this point is linear in A and B, it has no squares or no like sines or logs or anything, then it should be obvious that we're looking at a straight line for our subset S. Therefore, we use the work from part 4 to proceed. We can write this as being equal to x and this as being equal to y, and then we can solve the corresponding equations to find the required line. So if we do that here, we get a plus 2b minus 2 over 5 as being equal to x, and we have 2a plus 4b plus 1 over 5 as being equal to y. Then we can multiply by 5 to both sides on all of these equations and add across the required constants to get 5x plus 2 equals a plus 2b, and then 5y minus 1 equals 2a plus 4b. We want to eliminate a and b from these equations to get a particular line because this result holds true for every value of a and b in the entire xy plane. There are various ways to do this, including choosing some points a and b to consider. However, in this case, a particularly nice way is to notice that the expression here is exactly half of the expression here, and therefore we can eliminate a and b quite swiftly and immediately. We get 5y minus 1 is 2 lots of a plus 2b, but a plus 2b is 5x plus 2. And so a and b have been eliminated in this equation here. If we rearrange this, it turns out, and I'll leave it as an exercise, that we get y equals 2x plus 1. The entire line is included in this set because we can vary a and b to be any point in an entire xy plane. And so if we describe this set S, we would have the line y equals 2x plus 1, and we have all of the x values being in R. This is to distinguish from a subset of this line being the set S. Namely, we could have all of the x values between -1 and 1, and that would give us a line segment. However, because we have all values of a and b that we can consider in the real numbers, then correspondingly, this gives us a line over the entire real numbers for our set S. Lastly, let's discuss the final part, part 6. This asks us to suppose that S has the property that for any 2 points P and Q in S, the line segment PQ is also in S. Out of interest, this means that S is called a convex set. Show that for a given point AB, there cannot be 2 distinct points of S which are nearest to AB. So, we can proceed essentially by contradiction. We can suppose that P and Q are 2 points which are in S, and they are also the nearest points to AB. Now, because we have 2 distinct points, we can consider the line segment PQ. Because of the property given in this question for this set S, all points along this line segment PQ are in S. So write that down. All points along the line PQ are in S as well, not just particularly the endpoints P and Q. Now, we have these points, say P and Q. We have our set S which must include all of the points on this line AB here. And say we draw, this is P and Q, say we draw our AB point as being here, then it turns out that if P and Q are distinct points, there must be a point somewhere in between them that is even closer. This is because the distance function, which we looked at earlier for straight lines, between P and AB and Q and AB must take the same value for P and Q because they are both the nearest point. And so they must have the same distance between here and here and here and here. But then we get a quadratic which has the values being the same at the two endpoints P and Q, but then because we have a quadratic with a unique minimum, as we saw in the previous part, I believe that was part 4, there must be a point in between which gives us a unique minimum. Alternatively, if we relax the assumption that P and Q are definitely distinct points, then this would lead to P and Q actually being the same point, i.e., even if we assume that we have two nearest points, in fact, they are the same, and so we have a unique nearest point to AB. Hopefully, you can construct that into some writing that you would use to answer this question. And if you found this content overall helpful, then please consider liking and subscribing, as well as checking out our full Udemy course. The link is in the description. Thanks for watching, and goodbye for now.